Okay, let's get started. I have been gradually updating your homework assignments, as some of you have seen. So just as a rule of thumb, we'll say that it'll be finalized by 5 p.m. on Monday. Once 5 p.m. Monday goes by, I'm not going to add anything else. But I will continually on Friday, maybe over the weekend, I'll continue to be adding to the set. So you always want to be working on it. Don't wait till Monday or Tuesday to start, okay? So the last thing that I added was, well, so we're going to do, here and there, we're going to do this, use the online homework system called WebWork. So that's part D. So let's just take a look at that real quick. So if you go to, and right below Wednesday's homework post is the startup instructions for WebWork. So this is just the very minimal you'll need to get going, get started. So let me just point out the preview answer button is extremely helpful. Use the preview answer. It'll give you some hints and clues about what you've entered that might allow you to save an attempt, okay? And then email instructor. If you have questions, don't start an email thread from your inbox. There's an email instructor button at the bottom of every problem page. Use that button because then I give a direct link to your problem, okay? If you need to take a snapshot of the work you've done and attach that or send that in a separate email, that's great. But always use the email instructor button if you have questions. Yeah, so that's below Wednesday's homework post. It gives you all the basics for getting started and getting going in it. But it looks like this. You're going to go to, make sure you go to 271, not 272. Sign in. And you see, you'll only see one thing. You'll just see integral as signed area. Click on that. You've got 5 problems. It'll show you how many attempts you have remaining. For multiple choice, matching, true-false type questions, there'll be less attempts, so be aware of that. And then I just want to show you that you can, when you have open-ended, like free response type, you can put in expressions. For instance, 3 plus pi squared divided by 8 plus 40e. Okay, and so here I put this expression in, and so instead of using that as an attempt, preview the answer, and it's going to tell you, rut-row, you're missing a parenthesis, something's wrong. See, I just found that out without wasting an attempt. Okay? So it's like, okay, I don't want those parentheses, so get rid of that. So I want to do that. And then I preview answer again. And I look at it, and I say, no, that's not what I wanted. I wanted 3 plus pi squared all over 8 plus 40e. You see? See all this information I'm getting without using an attempt. Okay, so let's see, how do I want to get, I want it to be like this. I want to divide by this whole quantity. Now preview again. Still haven't used an attempt yet. Nope, that's not what I wanted, right? I wanted 3 plus pi squared in the numerator. I didn't want 3 plus the fraction, so I need another set of parentheses. So it's the preview answer not only gives you little, hints, but it also will give you a nice image. That's what I wanted, okay? That's what I wanted. And then it gives you a decimal approximation. So put in expressions like that. Don't punch that expression into your calculator and then try to guess how many decimal places at once, right? If you just put that expression in and get it looking right, then let WebWork be the calculator, okay? So, okay, that's definitely what I wanted, and that's definitely wrong, right? Okay? So then, now I've used an attempt, and it's telling me which are correct and which are incorrect. And so you've got, on these, usually on open-ended or multiple answer questions, you've got 7 attempts. And that's to help you deal with the technology, right? You should be, if you're understanding it, you should be getting it right in the first couple attempts, okay? If you're on attempt 4 and 5, something's wrong, get help. Don't wait till you've wasted 6 attempts. Get help if you need it, okay? Questions about WebWork? Okay, and so for this particular assignment, I have an extra little written. There's a lot of explanation here, but it's not that much work. Okay, so there's this additional like little writing exercise you're going to do about that web work exercise. So from your web work homework, for each of these down here, so there's from number 1, 3, 4, and 5. In your own words, interpret the definite integral. So a definite integral means you have a value at the bottom, the starting value, and then rather than having the independent variable at the top of the integral, you have another value, right? That's what we call a definite integral. A definite integral. But really, that's just like the functions we've been doing, evaluated at a particular value of the independent variable, right? So that's the way I want you to look at these, because in this web work, there's no net accumulation functions, right? There's no integral functions. It's all these definite integrals. So I want you to get practice at when you see a definite integral, you want to think of it as a function that's being evaluated at a particular value. So here's an example. All right, so all problems are of the form of a definite integral rather than an integral function. For example, the integral from 1 to 2.4 f of x dx, that was what all your web work problems are going to look like. But we really focused on this idea of accumulation functions. So how does that relate to an accumulation function? So here's one way to explain that. This is the function value, capital F of 2.4, where capital F of x equals the integral, or the net accumulation from 1 to x of f of t dt. Capital F gives the net accumulation of signed area for the graphed function f. Remember we said, what's the rate of change of signed area? What's the rate of change of signed area? This is like the most important thing of the whole last 2 days. The rate of change of signed area is the value of the function. We worked on that for 2 days. Okay? That idea, you better believe it's going to be on the test in multiple ways. If you have a function and you want the signed area between that function and the x-axis, the rate of change of that function is the value of the function. Okay? So f gives the net accumulation of the signed area for the graphed function f. Capital F of 2.4 is therefore the net accumulation of signed area of f as x increases from 1 to 2.4. So that's just a way of describing this definite integral as one particular value of the net accumulation function. So I called it capital F, so that would be capital F of 2.4. Does it make sense? So you're going to do something. This is not an exercise in copying my version of it. You got to do it in your own words. In your own words, okay? You're going to practice doing this in your own words for these ones that I've specified here. One from number 1, from number 3, 4, and 5. So again, that's a lot of explanation for a little bit of work, but you need to think about it. It's not an exercise in copying my example, but my example is there, okay, on the recording, okay? So it's all being recorded right now. So you're going to complete the set, do these extra little written exercises like what I just showed you, and then today I'll add more based on today's lecture, okay? And that'll be the last thing. 5 p.m. will be cut off, right? It'll be finalized. Questions about the homework? And then we have office hours all day today according to the schedule, and tomorrow. So today, so I won't read it to you, but it's right there on Blackboard. And let me make sure. You guys, are these accurate times and places? You're good? Both good? Okay, so this is it. And please note that mine has changed from the beginning of the semester. It's no longer afternoon, but 11:15 to 1 on Tuesday. Okay? Please note that. I had it more like 1 to 3 before, so now it's going to be 11:15 to 1. Okay, so definitely get going on the homework if you haven't already. You're kind of late getting started if you haven't, but get the support you need, okay? Any questions about the homework, office hours, any of that? Yes, please.
How's the web work?
Can you guys come hand these out? What's that?
How's the web work graded? Do we get like points off?
Yeah, you'll see. So when you get it right, you get it'll show green. Like if you get the whole thing right, you'll see a green bar. There's nothing else to do. You're done. You got credit. And then basically at the end of, so you'll have a web work grade and a homework grade and a written homework grade, and then I'll combine those to be your homework at the end of the semester.
I was wondering, like, do we get like less credit if we use more attempts?
No. If you get it completely right on the 7th attempt, you get the same credit as if you got it right on the 1st attempt. Yeah, you don't get less credit for trying it, for missing it a couple times. Other questions? Okay. So let's begin a sheet. The side you want is the area side. What does it say at the top? That side. Yeah, so the side that has the date on it at the top. It looks like this. This is page 1. This is what we'll do first. So the beginning is review. So the beginning is review. See if you've got the main gist of the last 2 days. And then where we're transitioning into today is we're going to start talking about using integrals for volume, accumulation of volume functions. All right, so we're going to be setting up some situations where we're going to create a solid or create a shell, and we're going to fill up that shell, like a 3-dimensional shell. And we're going to fill up that shell. We're going to accumulate and fill it up with some type of elements. And then our accumulation function will be a volume accumulation function. So that's where we're headed. And so we're transitioning into that today. So we'll start with the first, just do the first 2 parts there. When you get to right cylinders, so you can try it, but we'll talk about it after we discuss these first 2 parts of page 1. Then I'll explain a little bit to you about right cylinders, and then you can go from there. So just the first 2 boxes on page 1 should take about 5 minutes. 5 minutes to do that. Okay, I'm going to have a call-on sheet, but let's just spin the wheel here. Neil, you're up.
The whole thing?
No, just the first part. So the rectangle area grows at what? A constant rate of change of? 4. You said a constant rate of change of 4. Agree?
Yeah.
And what does that mean if it's a constant rate of change of 4? Miriam. Where's Miriam? Yeah. And what does a constant rate of 4 meters per second mean? So that's what we're getting at. What does it mean if there's a constant rate of 4 meters per second? Neil, back to Neil.
Any change in length will result in an area of 4 times that change in length.
He said any change in length will result in an area of 4 times that change in length. Oh, so close. It's really, really good. There's just a little, so he said any change in length will result in a change in area. Right? It's not that the final area will be 4 times that change in length, but the change in area will be 4 times the change in length. So subtle but very important difference, because those are 2 totally different quantities, right? The total area and the change in area that you get from a change in length, totally different. Okay? So yeah. So but it was you had the spirit of it, right? Given any change in length, the change in area that results will be 4 times that change in length. This should sound like a broken record a little bit, but it's really important, this idea of rate of change. Okay, let's see how we did in the second one. Let's go back this way. Where's Adam O'Reilly?
Right here.
Adam.
That's a changing rate of change.
Okay. Okay, goes a changing rate of change of, and what is the value of that changing rate of change?
It looks to be around 3.
Okay, 3. So is it changing at a rate of change of 3?
Well, it's changing at a rate of change around 3.
But what? For this current value of x.
Right.
So how could we describe what the rate of change is for any value of x?
Interchange
Not the rate of change. Not the rate of change. Yes, sir? F of x. F of x. So, changing rate. Okay? And so if the rate of change, the changing rate of, so f of x, right? So for any value of x, that rate of change would be whatever the value of the function is.
Would just stating f be acceptable? Or?
No, so f, okay, so some just a little terminology here. If you say f, what you're talking about is the whole function. You're talking about this relationship of independent variable and dependent variable. It just kind of, it's a name for the whole function. So what is the rate of change? The rate of change is the whole function. The rate of change is just the dependent variable, right? It's just what comes out of the function, and that's where function notation comes in, right? Function notation is now specifically a value. This is not a value. This just is a symbol that represents the whole function, everything about it. This now is a particular value, right? What value is it? It's the value of the dependent variable when the independent variable is x. And that was the whole point of function notation, and we'll see it all semester long. That's why we reviewed it in the first week. Does that make sense? Yep. So know the difference between just saying f, which is kind of just more abstract, like this function, right? This function, everything about it. It's the name of it. And then f of x, now we're getting into the math, and we're saying this is a value of the dependent variable. That is a value, and that's why we can quote it as a number or a value, right? It's the value of the dependent variable when the independent variable is x, or whatever's in the parentheses. Okay, so what does it mean that the rate of change is f of x? Jillian? Yeah? Okay, region's area is varying, so going back to our definition for rate of change. Avi, last and the first. Avi, so what does it mean that the rate of change is f of x? Well, what is the meaning of the rate of change? What is the meaning of the rate of change? Ingrid. Okay, so not at any given x, but given a, not value, change. So for a change in x, you want to go ahead? Yeah.
Yes. For any change in length, the corresponding change in area is the rate of x times the change in length.
Good. So said for any change in length, or then that would be a change in x, the corresponding change in area would be f of x times the change in x that you picked. Is it right? Yes and no. So the idea is right, but there's something that's not correct about that. What do we also need to say? Yes, sir.
You have to say that it's only over very small changes.
This only works if the change is really small, right? This time it only works if the change is small. The change in x is small. Because what if you take a big change in x? Are you going to get the actual change in area? No, because that rate is changing, right? For a constant rate, it doesn't matter how big or small a change of x you get. You can always say that that change in area will be 4 times the change in x, no matter how big or small your change is. But now if you've got a changing rate, remember this, you can only really say that you get an accurate change in area if that change in x you picked is very small. Remember, we had to zoom in and see all those little steps of the function. But if you pick a large change in x, say from here to here, well, then you're going to take this rate, and what are you going to do? You're going to accumulate at that height for that, and you're going to get that area. Is that going to be the right change in area?
No.
Too big or too small? That's going to be too small. Right? But if I pick a really teeny change in x, then we can say virtually it's a constant rate in that little change in x. It's virtually constant rate. So let's go back. If I pick a really small change in x right there, then we can say, oh, it's essentially constant right for that little change in x. and it's a constant of the function value, and now we get an accurate value of change in area. So that's important. Does that make sense? Okay. All right, so we want to talk about, so that's review, but we'll actually kind of come back to that a little bit. When we talk about, we're going to start talking about volume. And the first thing we want to talk about volume is understanding what is a right cylinder. What is a right cylinder? So a right cylinder means you can start with any shape you want. So I'll start with a square. And you guys will just imagine your own here, but I'll start with a square. And you're looking at it kind of above from an angle. So imagine that that's a square. You're looking kind of down on an angle at it. And what's a right cylinder? So a right cylinder means we're going to let that cross section just remain the same, and I'm just going to, it's just going to go straight up with that same cross section. Just go straight up with that same cross section. It's the worst and the best right cylinder I've drawn all day. Okay, but so the idea is, and it doesn't have to be a cube, so that kind of makes it think it's a cube. So let's make it a little smaller here. So start with any region, and you just extend it perpendicular to the plane of that region. Extend it at any length perpendicular to the plane of that region. So here's. So it does not have to be circular. So sometimes when you think of cylinder, you think circular. Doesn't have to be circular. Okay? It can be any shape, any region. And then there's a plane for that region. So then if you extended that region perpendicular to that plane so that all cross sections are that same, that same region. That one's the same. When I say cross-section, I mean like horizontal slice. Every time you slice it horizontally, you're going to get that same region you started with, all the way to the top. That's a right cylinder. Right meaning we got the perpendicular element. Okay. So you're going to draw some. So meaning you can do any shape you want, but then it has to that shape has to be this, and then any height you want, but that shape has to be the same cross section all the way up through. Okay, and then you want one of them with a circle in it, with a hole in it. So for instance, I could do. You could do a triangular thing, and then you could have an oval in it. So you can reproduce that. So I've got kind of like a prism, like a triangular prism, but that's a right cylinder, and it's got a hole in it, so water would just fall right through it. There's another example. So you're going to just draw 3 of these, just for practice. Just draw 3. And one of them should have something with a hole in it, okay? So any shape you want, just as long as it stays that shape through the length of it, or the height. Okay, questions about that? So if you want to check with us later, we'll walk around later if you want to check on yours, that's fine. But the key is that no matter where you slice it, you're going to get the same shape. You're going to get the same base region, no matter how you slice it, like my red slices there in the first one. Okay, does it make sense? Okay, so is it a right cylinder? Yes or no? Is it a right cylinder? Yes, right? No matter how you slice this thing, you're going to get like a flat ring, right? You're going to get like a flat ring, like the yellow, right? The yellow is showing the base. And no matter how you slice it, you're going to get that same shape as the yellow ring. Okay? So now these cylinders are going to be, the majority of the problems we're going to do are going to be these are the cylinders that are going to accumulate to fill up a shell so that we can write a accumulating volume function. So we're going to be accumulating volumes of these things. Accumulating volumes of these things to fill up some empty shell and have an accumulation function of volume filling up that shell. Does that game plan kind of make sense? So most of the ones we'll do will be like this. But now there's two ways that these can accumulate. So watch. Right? So the shells can change by changing their height, or the shells can change by changing their radius. See that? So the shell we can see changes in the shell by changing its height and keeping its radius fixed, or changing its radius and keeping its height fixed. So what our goal is for the rest of the class today is to figure out what is the rate of change of volume in each case. So in the first one, what's the rate of change of volume with respect to changing the height? What's the rate of change of the volume of that thing with respect to changes in height? And then what's the rate of change of the volume of that thing with respect to changing its radius? So this worksheet is going to kind of guide you through that. So the first thing you're going to need to do, and I'm just going to leave that thing running, okay? That's just going to run so you have a visual. The first thing we need to do is figure out, so here's an example. So you have on the back of your sheet now, you have an example of one of those. The inner radius is 2.5 meters, the outer radius is 3 meters, and the height is 7 meters. The first thing we want to do before we get to the rate of change is, can you just write an expression for the volume of that thing? Just the constant volume of the non-changing cylinder. That's going to be crucial. So just an expression. Don't do any simplifications or calculations. Just write out like the expression that you would type in GC or in your calculator that would calculate that volume. Make sure you have that right before you go on. Check with me, check with a TA. Make sure you have question A right before you go on. How do you calculate the volume of that? Hold on a sec. And then we'll move on to part B, and we'll work on the height increasing. So I'm going to lead you through this. You need to write an expression for the change in volume if the height increases by 0.4 meters. So you're going to be, so first of all, how do you represent a change in a quantity? And then you're going to use your basic volume that you did up in part A. All right, and then what is the change in volume if the height increases by just any change, DH? It's not on your smartphone, and it's not on your laptop. Okay? Here's the key. That's what you should have gotten for the volume just of the static cylinder, just this solid cylinder that we started with. It's the big cylinder minus the hole, right? It's going to be the big cylinder minus the cylinder that's the hole. So that's going to be the basis of finding changes in volume now. You're going to use that to find changes in volume. And in general, what's a change in volume? What's going to be your... No, just very general. How, just in the most general sense, how are you going to calculate a change in volume? It just has to do with volumes, what I'm asking. All it has to do with is volumes. How do you get a change in volume? Final minus initial, right? Final volume minus initial volume. So that's going to be how you're going to calculate the change in volume. So you're going to do that for 0.4. You should be working on that for 0.4. And then for DH. Okay, so we'll regroup in like 2 or 3 minutes so we have time for the whole thing. in our room. Okay, how'd you do? Check what you wrote. Am I missing a decimal? Oh yeah, thanks. Just didn't pick up. Is this what you wrote? So your volume final is going to look like that same one I wrote, but with 7.4s in there because the height changed up to 7.4. And then the volume initial is just what we wrote, right? The volume initial is just what we wrote. Questions on that? Don't worry about numbers. Don't worry about. There's no calculators involved here. We're going to do a little algebra, but don't worry about that. We're not calculating answers. Okay. Okay. So then the next thing it asks us is, what's the rate of change of the cylinder volume with respect to cylinder height? How are we going to find that? So what is our frame? How do we frame a rate of change? How do we frame rate of change? If we want to find the rate of change of volume with respect to height, that is framed how? Is that a hand? Want to try?
Would it be just the same with just instead of the actual measurement, like DH?
Maybe. You gonna try?
Doing the same thing with 7.4 and 7 plus DH, and then like the initial.
Okay, so that's how we're actually going to figure out what it is. That's right. That's how we're going to figure out what it is. But just if I could write down something that would frame the meaning of the rate of change, say in that box right there. Yes, sir.
I'm thinking that you'd probably say that the change in for every value of the change in height.
Okay, for every volume of the change in height.
And we have the dV value.
dV is. It's the same thing again, yeah. dV equals m times h, dH. This frames our meaning for it, right? Because what we're saying is, here, let me write it down here so you can see it. dV equals m dH. Because this is the equation form of this thing we've been saying. It's the equation form of this thing we've been saying. Giving any change in height, the resulting change in volume will be m times that change in height, right? So that's the equation form of, it's the same as dy equals m dx, right? But now we're talking about a change in height and the resulting change in volume. And so this is kind of the math language version of this thing we've been saying, explaining rates of change, right? So this frames our meaning for rate of change. Given any change in height, the corresponding change in volume is m times change in height. Okay, so yes, and someone said, tell me your name again? Hannah was saying we should do what now? So if we want to do dV for d, so that was for 0.4, dH equals 0.4. So what about just generically for just any dH? Then what would this be now for any dH? So what would it be? What would be different here? So for any dH, not just 0.4. Yeah.
Just substitute any fractions of 7.4 with 7 plus dH.
Okay. Right. So I'll do this in red now, so you can see the difference. So with dH, it's going to equal this change in volume. It's going to equal pi times 3 squared times what? 7 plus dH minus pi times 2.5 squared times 7 plus dH minus the same original volume that we had, right? So this would be the same. So look, if we could change this thing right here, see this whole big thing we wrote? If we could get that to look like something times dH, then we would know what the rate of change was. You see that? If we see, because that's dV, right? That's dV for a change for a dH. So if we could get that whole long thing I wrote in red to look like mdH, then what we multiply dH by would be the rate of change. Does it make sense? So how can we do that? So do you see that if you multiply through pi 3 squared times 7 and pi 3 squared times dH, do you see that that pi 3 squared times 7 will be then minus the pi squared times over here? See that? So I can multiply this out. And then this part will subtract off with that part right there. And they'll go away. Question? No. We're just doing algebra. No, we're just doing algebra. Okay? So if I multiply this through, but that is a way to do that. You're right. That is a way to do that because this is, yeah. But that's not where we're going. Okay? And then similarly, if I multiply this thing through, that right there will subtract off with this. And so then what will be left? It will be left pi times 3 squared times dH minus pi times 2.5 squared times dH. So it would get too ugly if I wrote everything out. Can you follow the algebra in your head there? So it's going to be pi times 3 squared times dH minus pi times 2.5 squared times dH. We're almost there, right? We've almost got something dV equals something times dH. Okay? So what is that something? So can we now write that as something times dH? Pi times 3 squared minus pi times 2.5 squared. So what is the rate of change? In this case, for this particular cylinder, if its height changes, what's the rate of change of volume with respect to height if we change its height for that cylinder? Don't worry about calculating things. Just expressions are fine, right? So what's the rate of change? Yeah.
Pi parentheses 3 squared minus 2.5 squared.
Yeah, this thing right here. That's our M. Now, here's the key point. So that is the rate of change. So in general, that's what? Pi times outer radius squared minus pi times inner radius squared. What's that? What is that right there? What is pi RO squared, radius outer squared, minus pi radius inner squared? Tell me about looking at this.
The area of the base.
It's the area of the base. It's the area of the yellow ring. So if you're changing the height, the rate of change of volume is going to be the area of the base. The area of the base of your cylinder, the area of that yellow ring. In this case, the area of that yellow ring. Super important, right? If we've got a cylinder and we change its height, what we're saying is the rate of change of volume with respect to height is going to be the area of the base. In this case, the area of the yellow ring. Okay, so how does that relate back to question 2 on page 1? So how is that kind of the same as the rate of change of signed area when you have a changing function? Something to think about. All right.